Welcome to Oddly Real. I'm Nem Stefanovic. When we look out into the cosmos, as well as here on Earth, we see matter arranged in fascinatingly different forms. This includes planets, stars, and galaxies, as well as air, oceans, and landforms. It also includes life itself. All of these things are made of normal matter. Yet, surprisingly, there's an entirely different form of matter, a kind of mirror image of our normal matter, called antimatter. Antimatter and matter, although similar, are essentially complements of one another. And when they come in close contact, they annihilate each other in a spectacular destruction that converts their masses into pure energy. However, anywhere we look, on Earth or in the universe, antimatter is nowhere to be found, except for a few processes that produce fleeting amounts. Our universe is made of normal matter, yet the laws of physics and the nature of spacetime demand that antimatter must also exist. In this episode, we'll learn about the amazing properties of antimatter and its place, or lack thereof, in our universe. If you were to look at something made of antimatter, you wouldn't be able to distinguish it from normal matter by its appearance. On the surface, it would look the same. However, if a matter particle and antimatter particle come into close contact, they annihilate each other to release a large amount of energy. In fact, their masses are converted into energy according to Einstein's famous formula E equals mc squared, where E is the energy, m is the total mass, and c is the constant of the speed of light. This violent reaction between matter and antimatter is detectable as high energy radiation, like gamma radiation. Here on Earth, we're surrounded by normal matter, so any antimatter would not last long and would quickly be annihilated. So it's safe to say that Earth is made of normal matter. This is also true for our solar system. We've actually sent out satellites and robots to its far reaches, and in every instance, all we've detected is normal matter. But what about the rest of our universe? If we look out into the cosmos, how would we know that stars or entire galaxies aren't made of antimatter? If stars or solar systems were made of antimatter in our own galaxy, we'd be able to detect significant amounts of gamma radiation from the annihilation reactions taking place between the surrounding matter and antimatter. In general, this is not the case, and so our own galaxy is made from normal matter. If we look at galaxies away from our own, we'd also expect that those galaxies would produce gamma radiation signatures as their boundaries interacted with surrounding intergalactic dust and gases, which we also do not see. We can zoom out even further to look at whole clusters of galaxies and specifically focus on the boundaries between these clusters and other clusters of galaxies and their surrounding dust and gases. Yet again, we detect nothing to indicate the presence of antimatter. In fact, everything we see up to at least 100 million light years around us demonstrates no significant presence of antimatter. As far as we know, the visible matter in our universe is made primarily of normal matter, not antimatter. But is it possible that antimatter is a major component of the universe that is further away than we can see? This is a possibility, but there's one major problem with this idea. In order for that to be true, there'd need to be a mechanism to separate matter from antimatter in the early days of the universe, so that the two types did not annihilate each other right away. However, there's no established mechanism for this to occur. Thus, we appear to live in a universe that is only dominated by matter. Despite the presence of normal matter in our universe, there are some natural sources of antimatter. Our sun's core has a temperature of approximately 15 million degrees Celsius, which separates hydrogen atoms into a plasma consisting of protons and electrons. As part of the nuclear process that fuels the sun to generate heat and light, protons can change into neutrons, which also emit positrons, which are the antimatter equivalent of electrons. The positron is quickly annihilated with one of the many surrounding electrons to create gamma radiation. This radiation travels out of the core of the sun, passing through the sun's outer layers. The gamma radiation gets absorbed and re-emitted many times by collisions with electrons, over hundreds of thousands of years before it actually emerges from the sun's surface. At this time, the original gamma radiation energy is reduced so that the emerging radiation is in the visible light spectrum. So daylight is actually a result of matter and antimatter annihilation. Another example of natural sources of antimatter can be found within our own galaxy. There are clouds of positrons, which are antimatter, close to the center of the Milky Way galaxy that we can detect from their gamma ray signatures. However, this is an extraordinary situation that happens around X-ray binary stars. These are normal stars that are being consumed by neutron stars or black holes. Their gases are pulled away and spiral into the consuming entity, causing the gases to heat up, generating pairs of electrons and positrons. There are more examples of antimatter generation as well, including the natural decay of radioactive substances such as certain uranium isotopes, which happens right here on Earth. Human beings are also able to produce antimatter in small quantities using particle colliders. Antimatter provides a means to unlock vast amounts of energy that is significantly more efficient than other energy conversion processes. A matter-antimatter annihilation reaction has the potential to convert 100% of a mass into energy according to the formula E=mc². For example, 1 kilogram of antimatter, when annihilated, produces 10 billion times more energy than the detonation of 1 kilogram of TNT explosive. Additionally, an antimatter annihilation will produce 1,000 times more energy than an equivalent fission reaction per kilogram, and 100 times more energy than an equivalent fusion reaction per kilogram. What exactly is antimatter, and why does it annihilate with matter? The existence of both matter and antimatter is rooted in both quantum mechanics and the nature of spacetime. One way to think about it is to first consider a vacuum in space. Instinctively, our nature is to assume that space is empty. If you put a particle there, we can say that the particle is associated with some energy, as per E=mc², due to its mass at rest. Thus, we associate a vacuum with zero energy and the presence of matter and energy as positive or greater than zero. However, the vacuum can also have states of negative energy, less than zero. For example, take the energy of an electron particle, but remove it from the vacuum. Then the vacuum has lost some energy and there is a hole there. There is an absence of some of that negative energy, with a removed negative charge of the electron particle that was taken out. This hole now will appear like a particle that has positive charge and with all the same attributes of the positron. In other words, antimatter. In fact, we can think of the vacuum of space as being a vast bottomless sea of negative energy. How would an electron, for example, be removed from the vacuum? This requires energy. A high energy photon, like a gamma ray, can be used to knock out an electron, turning it into a conventional positive energy electron particle. Additionally, this would leave a hole in the negative vacuum energy, an absence of negative charge, which would manifest as a positively charged positive energy particle, the positron. Conversely, if the electron and positron recombine, the hole is filled and the high energy photon energy is released again. Higher energies can knock out even more negative energy from the vacuum to produce even heavier particles. Notice that there is also a symmetry to this action, since we expect that for any matter that is created, there is associated antimatter to balance out the energy. Antimatter particles exhibit a symmetry between positive and negative charges, and every particle has an associated antiparticle. Even a photon, with zero charge has an antiparticle, being itself. Photons are their own antiparticles. The annihilation reaction between matter and antimatter is extremely useful for discovering different types of particles. Two particles, one matter and one antimatter, can be accelerated to highly energetic speeds and made to collide, causing annihilation. The large amount of kinetic energy from the collision can result in the creation of a wide range of heavier particles, such as muons, taus, quarks, and more. Interestingly, experiments have shown that some particles, like pions and kaons, exist that are neither matter nor antimatter, but combinations of both. They are a mixture of a quark and an antiquark. They do not last long, since the quark and antiquark in close proximity annihilate almost immediately. It is also possible that a matter and antimatter particle, like an electron and a positron, can bounce off each other rather than annihilate. When an electron and positron are moving slowly, they can attract each other into a mutual orbit to form positronium. However, this is short-lived and will result in a quick annihilation. If a proton and antiproton approach each other slowly, they also start to orbit each other. The orbits start to drop energy levels, releasing gamma rays, until the particles ultimately annihilate within a short fraction of a second. It is worth noting that even whole elements can exist in their antimatter form, just like we would expect with normal matter. Antihydrogen is an atom composed of an antiproton and a positron, the mirror image of a hydrogen atom. In 1995, it was announced that 9 antihydrogen atoms were formed at CERN, the world's largest particle physics laboratory. By 2002, tens of thousands of these atoms were already being produced. Since then, even antihelium has been produced. It is not clear to what extent traces of antihydrogen or antihelium even exist in our universe. So this is an astonishing accomplishment for humanity, and something extraordinary that is happening here on Earth. When antimatter is created in a laboratory, it is possible to capture and store the material without interacting with matter. This is done by the use of electric and magnetic fields in a vacuum around tubes where the particles are kept circulating away from the walls, which are made of normal matter. This was accomplished at CERN using a tunnel 27 kilometers in circumference that could keep positrons for weeks on end as long as there was power in the system. Interestingly, there are also alternative devices like the penning trap that have been used to store one particle of antimatter in a container half the size of a human thumb. Another incredible aspect of antimatter is that antimatter particles behave the same way as backward time-traveling matter particles and vice versa. For example, if you take electrically charged antimatter particles, but run their motion backwards in time and look at them in a mirror with their charge polarities reversed, they would behave exactly the same as the normal matter particles. Both the matter and antimatter particles, when reversed in this way relative to each other, would respond to the same forces and laws of physics in the exact same way in our universe. One more fascinating discovery was made that shows that there are some interesting distinctions between matter and antimatter. For example, neutral Kaon particles can transform into anti-Kaon particles and vice versa, called neutral Kaon oscillation. A series of CERN experiments in 1998 showed that the anti-Kaon particles transformed into kaons at a rate that was slightly different than the reverse, kaons transforming into anti-kaons. This experiment was not unexpected, since it was known that other aspects of matter and antimatter violated certain rules of symmetry, resulting in Nobel Prize awards. In this case, there is an asymmetry, or a different behavior, between the matter and antimatter particles over time. At the subatomic level, we can distinguish in which direction of time, forward or backward, we are watching based on the oscillation rates of the matter and antimatter particles. Why does this matter? Well, in most cases, the laws of nature don't distinguish the direction of time. If you watch a particle move across space, you can't tell if it's moving forward in time or if it's a particle moving in the opposite direction with time moving in reverse. The laws of physics don't seem to care about the direction of time, and they are generally reversible in time. There's no arrow of time built into the laws of physics. The same laws work perfectly well in both directions. However, before you get too excited that Kaon oscillation is a proof of an arrow of time, I'll note one caution. When we talk about the arrow of time in general, we're actually talking about entropy and the irreversibility of processes. For example, we see eggs smashed to bits, but we don't see eggs spontaneously reconstruct themselves from the smashed states. Entropy is the major reason why our universe moves forward in one direction of time and not the other. This is distinct from the Kaon oscillation process, which is not directly involved in dictating the universe's path forward in time. Regardless, it's still quite fascinating to learn about how matter and antimatter can break certain symmetries, but it's not the same problem related to why time flows forward in general. Finally, there's a significant mystery that is the topic of ongoing investigation. If matter and antimatter form in pairs, then what happened to all the antimatter in our universe after the Big Bang? Theory and evidence from studies with antimatter suggest that shortly after the Big Bang, there was a slight imbalance between matter and antimatter. For every 10 billion antiprotons, there were 10 billion and 1 protons. The protons that remained from this great annihilation are what are left in our universe today. The exact mechanism for the imbalance is still a topic of considerable research and debate. Lastly, there have been some zealous suggestions that antimatter may possess the property of antigravity, or being able to fall upwards in a gravitational field instead of the normal downward direction. However, this is not the case, and antimatter, like matter, also falls down as expected. I hope you've enjoyed this episode, and remember, oddly real, really interesting.